tells me that I should work out things in slightly more detail, and that is what I am going to do now. And so just remember what we did. We started out with so we took a quantum mechanical system which was, let us take mass to be 1 square minus so whole square. So all these numbers are tailored to precisely what we had done with the king soliton. Okay, even this 2 I just went back and checked, and so I chose those numbers to be exactly that. We had done this thing. So the idea was to take t and to replace it with minus I tau, right. There was a minus, right, minus, we fixed the sign. Okay. So the question is, so the idea was that e power I s will go to, will become equal to, once you make this substitution, will give you the Euclidean action. And so the Euclidean action was simple to state, as Euclidean was just integral of d tau times dq by d tau whole square plus let us for completeness just call this quantity v of q. Later we will use this specific thing, but in general this goes through. Okay. And just note here is that this is, you just can compare this with the Hamiltonian density which you would have written for a 1 plus 1 dimensional theory when you are looking at time independent fields. This is the kind of thing which we had worked out long ago. So you can see that that if I identify tau with x and q with phi, these two actually look the same. Okay. So the idea was to look at a tunneling solution, and the tunneling solution for which this would be the Lagrangian. So you can see that Lagrangian is just t minus v in this setup. So it corresponds to a potential which is inverted, relatively speaking. Okay. So let us plot this now. Whenever I am plotting v of q, I will plot the one which I have written out there versus q, and so this would be okay. So now the idea is to evaluate, so the probability up to some normalization constant would be integral over dq e power minus s Euclidean by h bar, and the leading term will be up to, will be some constant times e power minus s Euclidean evaluated at the saddle point by h bar. Okay. Now the thing is that if you have many saddle points, in principle you should sum over all of them. Okay. But I am going to act as if there is just one saddle point. Even in this example there are many saddle points, as we will see, and so the solution, the the solution which will take you from minus a to plus a is so the way to understand this is to think of it as a limiting case of the following process. You assume that you have a very, very small energy epsilon which is tending to 0 from this side, and then there are turning points here and here. So you start your thing here, it will go like this, and if you take the limit when the energy goes to 0, these two will be the turning points, and it will actually take infinite amount of time, Euclidean time, to go from this thing. But we want to work out the solution, but this is just a very, very simple solution. There is a the energy, we can just solve it without, one integration comes for free because energy is conserved, and that would be just half dq by d tau whole square minus v of q. Okay. And for our tunneling solution E is 0. Okay. So, the American spelling for tunneling has one L, it bothers me, okay, but so I write double L, okay, but that is acceptable. So, what we have is that for the solution of interest we have half d square q by dt square equal to v of q. Okay. So, now the point here is to evaluate this action on this trajectory, and so that is what I will do now. I look at, so we need to evaluate the action SE at that on that saddle point, but now you can see that v of q is nothing but half dq by d tau square. So, I can plug that back in. So, S Euclidean on the saddle point, okay. One just one point here is that in this path integral at the boundary conditions are that at so that at some x q at some t initial equal to minus a and q at some t final equal to plus a. Okay. I could consider the opposite one, but that would just exchange these roles. Okay. So, S q of saddle point would be integral over d tau of, so that box quantity tells you v of q is the same as half dq by d tau whole square. So, I can just go ahead and substitute for how this thing would just become this would be just dq by d tau whole square, because half plus half is 1. So, I can just write it in this fashion, but I will write it slightly. Okay. And so, I have just traded one this thing. So, now you can see that the tau dependence. So, there was one question about boundary conditions, etc. You can see that it is sort of gone now. I mean, it is all we really need is that at initial time it is here and out here, and now we can go back to this and try to write it in terms of there is still a residual time dependence through tau, which we can get rid of by using this, but we need to figure out which square root to take. Okay. So, the square root should be, so you just take at some point it should be slightly positive, it should be moving, dq by d tau should be positive. Okay. If you want the other solution where it goes from plus a to minus a, we would choose the negative square root. So, dq by d tau will be equal to plus or minus square root of 2 v of q. Okay. So, we will choose this. So, let us call this, we will call this an instanton, and the opposite guy we will call it anti-instanton. Okay. So, this tells you we just have to choose this. So, we get S Euclidean evaluated at the saddle point is equal to integral from q equal to minus a to q equal to plus a dq of square root of 2v. So, you can go back and compare. So, what this cell tells you is that the probability is proportional to e power minus 1 by h bar integral q equal to minus a to q equal to plus a dq. Okay. So, this matches the saddle point answer which we had, because that had an e in it, and you just set e equal to 0, because that is our condition, and that is what you get. Okay. So, this agrees with the saddle point thing for this problem. Okay. So, this is the way of understanding how I mean there are prefactors etc., but you can fix all those things correctly, and if you want to you can look up some of the literature, for instance Coleman's lectures. Okay. So, that is what we get out here, but we can do more. We can actually evaluate what this guy is for our answer. So, I am going to be more explicit. Okay. Yeah. So, the saddle point. So, what is V of q in our example? It is just lambda over 2. So, 2 times that. So, that just becomes okay. So, what I get is that 2 V is what I want. So, this 2 will go away. I am left with the square root of lambda times square root of this thing, but I have to make sure that it is positive. In the region I should choose the positive, I should choose a square minus q square. So, this will just become dq square root of lambda into a square minus q square. Okay. We can just work out what this is. It is a simple integration. So, I can just do this. It is a root of a square q minus q cubed upon 3 evaluated between minus a and plus a. Okay. Both these limits will give the same thing. So, I will just 2 times evaluate this a cubed minus 1/3 a cubed, which will be 2/3 a cubed, that is a 2. So, it is just 4/3 root lambda a cubed. If you remember the king soliton had the same mass. So, recall several things. First, the king soliton okay, because there in the king soliton, sorry, this was not Hamiltonian density, it was energy. So, it was the mass of the what we call the mass of the soliton, that is what we got. In fact, we also saw when we were discussing Derrick's theorem that the king soliton actually satisfied this equation. Okay. So, you can see that the solution which we wrote in X space actually becomes the Euclidean soliton, it is the same. Okay. So, number 2 is that the king soliton satisfied, what is this equation? Let us call this equation satisfied star. Okay, plus sign was kink and the minus sign was anti kink, and here we will just call it instanton and anti instanton. Okay, satisfied star with of course the replacements, call q phi, and then tau becomes just space. Okay. So, now you can see that if I try, I mean there is no issue, I could flip things around, I could say that I could choose it like this, but that is not the same as flipping the limits. You also need to choose the correct solution, and that will also give you a minus sign. So, the answer for the same, you get the same answer whether it is the instanton or the anti instanton, the signs work out. Okay. I hope this addresses your question which you had asked me. Okay. So, it is one thing. So, at least you can see here in a very concrete example what we have seen is that in some sense our time independent solutions which we looked at, what were solitons in some d dimensions, could be thought of as a Euclidean thing in one less dimension in some sense. So, a soliton in d dimensions, d spatial dimensions, so by this this we would have said as time independent in d plus 1. This kind of appears like it has some relationship with an Euclidean instanton in some other theory, right, in a d dimensional theory. Okay, this is the kind of thing. So the key thing was that when you go from here, finite energy becomes, in this case finite energy gets mapped to finite action. But the quantity you are measuring is really the same, if you wish, it's just called something else. Okay. So what we are going to do is, like I said, we could have gone in so we followed a step, right. We went from 0 1 plus 1 to 2 plus 1 to 3 plus 1, and so in some sense you would say that fine, this is the end of the story, because we live in 3 plus 1 dimensions, we are not interested in higher dimensions. That is one way of thinking about it. But the point here this tells you is that maybe we should think about 4 dimensional objects. Okay. So and one more thing, what does this instanton do? It tells you that your actual ground state of your system is some coherent superposition of 2 different vacua. Okay. And so similar things, even instantons which we will look at now in 3 plus 1 dimensions will be of that kind. Okay. So let us go back to, so we return to 3 plus 1, because in some sense now if I give you a vortex solution or a monopole solution, I think you can just follow the crank, there is really nothing to do. Okay, it is just a saying that you just think of this thing as a solution in that theory. Okay. So let us get back to this thing. So the thing is that one interesting point is that you could ask, can we discuss something like an analog of Derrick's theorem for pure Yang-Mills? It is an interacting theory. Can we find finite time independent, so finite energy time independent solutions in say 3 plus 1 Yang-Mills? Okay. And so the answer is no. Again there is some scaling argument similar to that of what we did for Derrick's theorem, where we did it for a scalar field. Here you do it for the vector field, and this is due to Coleman, and you can show that really you cannot get finite energy solutions. Okay. So of course you can get finite energy solutions by adding other fields in the story, like we did with scalar fields, we added them. Okay. So we are talking about 3 plus 1 dimensions. Okay. So before that let us just fix some normalizations. For Yang-Mills fields, non-abelian gauge fields. So I keep using Yang-Mills and non-abelian gauge fields interchangeably. Okay. So the natural thing, so the Lagrangian we have written is something like this, minus 1 by 4 some g square f mu nu a f mu nu a. Okay. But we can also ask how to write this in terms of traces over, so we know that we can define something like this, f mu nu, we can this matrix valued object as f mu nu a times T a, where T a is as a generator of the Lie algebra. Okay. And let us choose these in the fundamental representation. Okay. So example would be for SU2, the Lie algebra SU2, T a's would be I sigma a by 2. Okay. We are going to follow the physics convention, which is to put the required things to be. Is this correct? Is it what we wanted to do? Do I want to do it this way? Yeah. So it has to be skew Hermitian, perfect, good. For SU2 it would be this, SU3 it would be T a's would be again the same thing. Okay. I would not lose sleep if somewhere else I have defined minus of this, that is not the I just want to get the i's correct. Okay. So this is what you want to get, and so this is in the fundamental. So this is 2 by 2, this is 3 by 3 representation. So we also know for all these cases trace T A T B. So let me do it for one of these cases. You get I square, which will make it a minus, and there will be half square, which will be 1/4 trace sigma A sigma B. I am just doing it for Pauli matrices, and so this will give you a. So we can rewrite this as follows. The standard trick is you write this as sigma A sigma B plus sigma B sigma A, and but that is equal to 2 times delta A B. So let me follow the thing twice. So this just becomes into half trace okay, and you should know this sigma A times identity in 2 by 2 matrix. Okay. So if you take the trace of this, you see that you get trace of this will give a 2. So it becomes 4 delta A B, which will cancel this 4, but you are left with a half. So this is equal to minus a half delta A B. Okay. So the idea here is that what I want to do here is to write the same action in terms of this guy, the matrix valued object. So now so let us look at what we get for trace so this will just, you can pull out the F mu nu A, F mu nu B trace. And we are going to work in the fundamental representation. So, but this is going the normalization, at least for these things, is minus half. So you can see this is equal to okay. So we can see that the same Lagrangian. So this implies that the Lagrangian can be written in terms of matrix valued objects as follows. Trace in the fundamental representation so it goes back to the same thing. Okay. So it is conventional to write the action like this in terms of in the fundamental representation, because if I choose it in some other representation you will still get delta A B, even the sign will work, but this constant half will become something else. So then the number, the prefactors will change, so the prefactors can be larger, etc. Okay. So I just wanted to fix this because I do not think I have fixed it anywhere so far in this course, so I just wanted to do it once and for all. Okay. So now we are, so the idea is now we are going to look for, so we need to look for Euclidean, so we solutions, finite action solutions in the Euclidean version of the theory. Okay, so we need to do the same thing which we did, and so let us do that. So first step is to take t goes to minus t equal to I tau minus I tau, and so for simplicity what I am going to do now is to do it for the abelian case, and then we can just the non-abelian case will just work out in some sense. Okay. So let us do that. So let us just consider abelian. Okay. So the action is still the same, but there are none of these A things, there is no traces, nothing. So let us see what we need to do. So first thing to realize is that so dt becomes equal to minus I d tau, that is good. Okay. Now what happens to f mu nu? So there are f mu nu can be broken up into two parts. There is f0 I, which is the electric field, and so that has a derivative. So f0 I is d0 ai minus di a0. Okay. So what we need to do is to make these two go the same way. So a0 also should be taken to, okay. The one way of understanding it, a0 comes with the wrong kinetic energy, so you need to flip that guy around, okay. But so let us look at how d by dt goes. This is just d by dt. So this should become so this goes to I plus I and you can figure out how the other one works out. So I just need to keep track of this. So what this tells you is that E goes to IE, okay. So and nothing happens to B. Okay, is this clear? Because there is no this thing. So the only thing which picks up a funny factor of I is this thing, and so you can see that the Lagrangian density was half E square minus B square, okay. And so what happens is no, this was correct, yeah, it is half E square minus B square, right. And so now you can see that if I under the Wick rotation, this goes to, this changes sign, so it becomes overall minus half of E square plus B square, okay. So the Euclidean action would look like S d4x half of E square plus B square, but this we should have guessed. It should look like the Hamiltonian density in one higher thing. We have worked out for general dimensions, we have worked out the answer was more or less, I mean, so it should look like this. This is what you get, okay. So now we have a Euclidean theory, and so what we want is finite action and last time we saw that so yeah, and now I return. So this is before I proceed here, I did this for the abelian case, but you can see that it goes through for the non-abelian case as well, okay. There will be just some extra pieces here and it goes through, there is nothing different about the whole thing, okay. So now the thing is we have to look for finite SE, and so the point here is that so you need f mu nu to go to 0 as on the sphere the 3 sphere at spatial infinity, at infinity, no need to call it infinity. Okay, and we saw that this implies that a mu must be pure gauge, okay. So we just go ahead and write a mu as at least this is what should happen for large r, okay. And we are in, it is a 3 sphere because this is in 4 dimensions, okay. This is what so there is nothing deep about the whole thing, and except now I have written in terms of the Lie algebra valued elements, you can see that is why it is easier to write. Otherwise if I have to write it in terms of mu a, it is a headache. That is one reason to go back to this. Okay, this is what we need to do. So in other words, configurations. So what we have is we have to study maps from S3, spatial S3, let us call it S3 at infinity, to the group G, because this G is a group element. Okay, and so this is classified by pi 3 of the group G. So somebody has to come and compute this, or we have to see this what this looks like. Okay. So first example is to take the abelian case, which is U1. You can show that there are no non-trivial maps which go from S3 to this thing. Everything can be easily deformed, smoothly deformed without any discontinuity or whatever. It can be smoothly deformed to the trivial one. Okay. So for G equal to U1, no non-trivial maps. Okay. In other words, there is no configuration, you cannot come up with a finite action configuration in some sense, there is nothing which is okay. So the next one is SU2, but for any non-abelian group this will go through. We will see for SU2 it is S3, but the key point is any non-abelian group always has a SU2 subgroup. So you could get inequivalent SU2s, which each of which you could so you could have many SU2s and you could generate different instantons or different sort of, not different instantons, different maps which go to the group. So you can find non-trivial elements, quite a few non-trivial elements. So if you find something for SU2, you are more or less sure to find it for any non-abelian compact group. Okay. So we will stick to only G equal to SU2, but we have already seen that the SU2 group manifold is you could write any group element as some what did I write? Yeah, I remember something I wrote, N0 identity plus Ni sigma I. Was it like this? Was there a half or not? There is no 2, that is what I am. It was this, and we saw that this arbitrary group element, and it was just N0 square plus Ni was equal to 1. So the group manifold was an S3, was a 3 sphere. Is this correct, or which 2 were you referring to, this 2 or this 2? There should be a 2 here. Huh? So that is an easy way for me to fix this. So I just look at e power I, yeah, theta a T a, we just expand it, right. So we just get 1 plus I theta a okay, and T a should be some I sigma a by 2. So there is no I, there is no I here either, correct, because T a will be have an I, and so that goes off. So that helps. So I get something like this, and there is no I here. Now we are in good shape. Oh, but actually it is very easy to check, you just say that this is unitary, right, you just do G dagger and check. If it is identity, it should, so, and this should be the condition for that. Okay, should I check it? No. Yeah, let me do that. Okay, so I get N0 square plus Ni Nj this term I am writing right now. So, it is fourth plus the other term which is N0 Ni. So, this does not cancel. So, I do need an I. I do need an I. Okay. Oh, we are doing a double, too many doubles. There is an I. Okay. So, there is an I. So, this clears everything. So, I just wanted to write it correctly once. So, what we see is that N0 square plus Ni should be equal to 1. So, this is a 3 sphere. Okay. So, we have maps. So, what we get here, so we have to look at maps from S3 spatial infinity to the group to SU2, and so let us choose some coordinates on S3. Okay. So, I will just choose, I will write something and then there should be 3 coordinates. I will call them phi theta 1 theta 2, you will see why I am choosing this, and this would go to group element which would be some g of phi theta 1 theta 2. Okay. And I will just state a result. So, the pi 3 of S3 is Z, which says that there is, for every integer you give me, I will give you, there is some kind of winding number. Okay. So, this is just a statement, and so now I have to construct for you G which has this property. So, the easy thing here is to just construct something. So, roughly speaking, what you want is, this is also a 3 sphere, you want all these angles to get mapped to these angles in some way, and I will just write out the group element. So, let us write something like this, G of some n be a configuration with, we have to define this thing, I will just call it winding number. N. So, whatever is this integer n. So, I have to write for you. Yeah.
So, this is why we end up soldering internal and space time.
Yes, exactly. That is where soldering comes. Yeah. So, what I will do for you is to, of course, G of 0 is the easiest one. I just choose it to be 1. Okay. So, I have to give you G of 1, and this is where you solder things. I just identify this with tau plus I times spatial and divided by R, where R equal to so this is the radial coordinate in 4 dimensions. Okay. So, I have to divide by this because otherwise it would have been square of this. So, I divide out by this. Okay. So, this if you wish, so this thing has is the analog of winding number 1, but the nice thing is, if you give me a winding number 1, now I can construct for you winding number n. Any ideas how? Act on it n times, right. So, if this is doing winding number 1, you do a further winding. So, I can just see that includes -1, which means take the inverse. Okay. So we can, so now we can see that we are able to write out configurations which in some sense have that winding number. I have not written for you what the winding number is, we will sort that out. I will give you a definition for the winding number, and so that will, so what we will see is that, so given this thing we can construct for you a mu with the same winding number and defined to be I okay. By the way, this is not the only way of writing this, there might be other ways of doing it, but you are guaranteed that this guy, if this has winding number 1, this will have winding number n. It just, yeah, inverse. I put an inverse there, yeah, okay. So let us see what this winding number would be. So this n will be some constant which we will determine in a moment times the following object, which is an integral over the 3 sphere at infinity. Choose some coordinates, so I will just call it as some angles. This d cube theta is this any set of these angles or some what is a natural measure in that thing times something like this. Okay. So I will just define this, but we could have actually gone and done it in a similar fashion to what we could have written this as coming from some integral over 4 space some conserved topological charge. We could do that, but I will leave that as an exercise for you. We will come back to this, but right now what I want to do is to show you how to fix this constant, and we will do that by choosing this guy, this solution, and working out the integral. That is what we will do. Okay. So first thing is let us choose coordinates. There is a coordinate independent way of doing things, but let me just choose coordinates on S3 for a moment. Okay. So what we will do is, so you start with usual x, y and z coordinates, and then there is the last guy which is tau. So what you usually do is to define an angle phi through this, okay, and then we define a second thing which we will call cosine theta 1, sin theta 1. Okay. So theta 1 and phi would be our normal spherical polar coordinates, but now the natural way to go would be to, in the hypersphere or the 3 sphere, is to add one more angle, and I just do the same thing. I just do this cosine theta 2 okay. Only thing I need to do is to work out what the measure is. I need to work out what the measure would be, and that you can do by showing that d4 of x, I will just call these as 4 variables. So from dimensional grounds there will be one radial coordinate, so I should have put that r also here, okay, and d4x would be on dimensional grounds would be r cubed d of r, okay, and so far we are written out something which is our normal thing. The other one I just need to write, there will be a d theta 2. So you have to work out the Jacobian, and this is what you get. Okay. So if you go to a next S4 dimensional sphere, you will have to introduce one more theta kind of thing, and that would just give you d theta 3 sin cube theta 3. It is a useful thing to remember. Okay. But coming back to this, the thetas, the way I have defined them, you have to check what is their limits. Okay. So the limits of these thetas, all the theta I go from belong to 0 and pi, they belong to the interval 0 to pi, okay, and phi is the only real angle. It's a goes from 0 to 2 pi, it's a circle valued object. That's why I use this different notation. It's worth remembering this thing, and once you give this thing, you can ask what is the volume. One of the nice computation to do is to do the volume of a 3 sphere. Okay, so the analog of so volume of S3. So I will not do the R integration, we will just forget about that. So, what I mean is volume of a 2 sphere is 4 pi. What is the analog of 4 pi for this? By volume I mean in that case it is the surface area. Okay. So, that for 1/3 and all came from the R integration there. So, that is not what I am doing, I am just want to do the integration over these things. So, these two integrals will give me, it is like an omega integration, will give me a 4 pi. So, I need to do only one integration, which is 0 to pi d theta 1, sorry, d theta 2 sin square theta 2. Okay. This is very easy to do because I can use the identity where it is 1 minus some cosine 2 theta, and that is an integral over the full this thing that averages to 0. So, this just gives me a half. So, there will be a half into a pi. So, it will give you a pi by 2. So, useful result is that it is 4 pi into pi by 2. So, this is 2 pi square. Yeah, there is one more neat point, which is suppose I make coordinate transformations. I have chosen this coordinates. This is not the only set of coordinates on the 3 sphere. I can choose anything I want. You go ahead, suppose you make another set of 3 coordinates and you work out how this transforms. What you will see is that because there is an epsilon, you get Jacobian, each of these will give you one thing, it will combine with this thing to give you the Jacobian factor precisely, which is the inverse of the measure. So, in other words, it is the answer is coordinate invariant, but this is to be expected because like I said, this you can think of this as arising from some topological charge, okay, which I have not shown. Okay. So, now we are left to, we need to really go back and evaluate this thing for this ansatz. Okay. Except now we you may think I need to know lot of details about this. Okay. So, the thing is but let us look at this thing, and so the claim here is that this object here I need to put it, this is a Lie algebra valued element. So, I should put a trace, I forgot to put that. And we are in the fundamental representation, right. So, this is what we will take. Okay. So, the claim here is that these guys G di G inverse, whatever happens here, this thing because of the epsilon I j k multiplying it, it will so this is like the answer will be only proportional to this epsilon I j k times some constant factor which we need to fix. Okay. So, how do I, yeah, okay. So, one thing we could do, first thing is to look at the trace of this thing, and these are all Lie algebra valued elements. So, I could write whatever you do G I d I G inverse should be some U I A sigma A. So, it is Lie algebra valued I by 2, this is what it should be. Okay. And so, now we let us plug this. So, this is not a deep statement, this is just saying that this is some Lie algebra valued element, okay. And we need to evaluate that, we need to fix what these UIs are, but for now the thing is now we can plug this into this and ask what this looks like. So, so there is a I by 2 whole square, a cubed, okay. So, this is what we have to evaluate, but what is this equal to? You can think of this as a 3 by 3, this takes 3 values, this takes 3 values. So, if you think of UIA as a 3 by 3 matrix, what does that mean? what is this object? It is a determinant. So, this is equal to determinant of u times epsilon a b c. Right, because I can just go ahead and take 1, 2 and put a b c to be 1, 2 and 3, and then I will get the determinant. That is the determinant, because a b c run over all those things. If these two are equal, any one of these two are equal, the answer will be 0. So, it is forced on you. So, this is what you get. Okay. So, you can see that now. So, we need to just evaluate trace epsilon a b c, but yeah, so that is sigma a, sigma b, sigma c, epsilon a b c, and this I can rewrite this as half trace sigma a commutator of sigma b and sigma c. Okay. What is the commutator of two Pauli matrices sigma a, sigma b? It is 2 I, this is equal to 2 I sigma a. 2 I epsilon b c d epsilon a b c, this is what we get d. Okay. And what is this? This is very easy to evaluate in the following sense. I can just by cyclic permutation I can make it b c a. So, this will just be delta a b a d with some factor, and that factor is just, so we can do that by just picking some value of c, pick c to be 1, then this can be 2 and 3. So, this is just 2 times, you can use the delta formula, but you can just evaluate it trivially, it is just 2 times delta a d. Okay. So, you get 4 which cancels with this. So, you get 2 I trace sigma a sigma a. Okay. But sigma a square is just identity. So, that gives you a 4 I. Okay. Are we done? So, now you can, I am going to erase this part. All we need to remember is that this epsilon with this gives me a 4 I. So, this I cubed will give a minus I, which will cancel with this. Which 3?
Sigma or a also. Sigma a, sigma n is 3
yeah.
times into 2.
Thank you. So, there is a 3. So, I missed out a 3, thanks. So, that is a 12. So, this is equal to, so 12 I, but this I cubed is minus I into I, which is plus I, divided by 8 into determinant of u. Okay. So, we stop here, hopefully there are no more errors. So, this is just 4/3. What am I doing? So, it is 3/2 determinant of u. So, the problem is just left to us evaluating what u of a is for this. Okay. I leave it as an exercise for you, but I will also work it out next time, but right now we just leave it at this. So, you can see that once we get this, we can actually work out. So, we will, what we want is to choose this constant such that you get 1 for this configuration. So, this is, I am not proving that this is the configuration, but I am just using this as a seed to fix this thing. Is that clear? Okay. So, I stop here and we continue next lecture, and next lecture we will see how these how to realize an explicit configuration which has this asymptotics. Okay. There is a very simple ansatz and you get a very simple solution.